Okay, wonderful. So we have done three methods. Today we are going to talk about Lagrangian methods, which is the fourth method. For solving constraint optimization problem. So once again, let me remind you, today we are going to be solving this problem. This is a problem I want to solve. I have a equality constraint problem. And so far, I think we have covered a few cases where you can convert an inequality constraint problem into an equality constraint problem. So even if you have inequality constraints, you can convert it to a problem of this type. Okay, so one of the algorithms that we have talked about so far is called the method of multipliers. Anyone remembers what this method is? It's also part of your assignment, or was part of your assignment. So I define my xk plus 1 or xk equals to argmin LC x lambda k, and then x is in Rn, and lambda k plus 1 equals to lambda k plus, let me put ck, hxk. Right, this is the method of multipliers. We talked about it maybe like earlier last week, if I'm not mistaken, maybe Monday or Wednesday. There is a problem with this method. Okay, so this method converges and everything. We looked at it. You've seen an example in your assignment, as well as you've seen an example on the board. So this method doesn't have any specific problem, but it doesn't have the problem with respect to convergence, but there is another problem, which is at every point of time, at every iteration, for every ck and lambda k, I need to solve this optimization problem, right? What does solving an optimization problem mean? I need to run infinite number of iterations, infinite number of gradient computation, infinite number of picking alpha k, infinite numbers of Armijo's rule, and whatnot. So if I were to ask you, I want to reduce the complexity of this algorithm. I don't like this algorithm because at every point of time, for every lambda k and ck that I've picked, you're asking me to solve this argmin problem, and I'm going to take infinite number of time steps in order to solve this problem. So I want you to simplify it. So can someone tell me a simpler algorithm? What would you do if you were in that position? Yes.
Maybe putting some threshold communication.
Some what threshold?
Threshold. At least we don't have infinitely many steps.
Yeah, you're going in the right direction, but how can you make it simpler? Now you have to pick lambda k, you have to pick ck. Now you are asking me to pick another threshold k. That's just too much for me. I don't want to apply my brain so much. I want simple stuff. I'm a simple man of simple thoughts. Yes, you have some thoughts? No? Yes.
For 1 Newton step.
Okay, you're going somewhere. 1 Newton step. I don't even want to do that. I'll just take 1 gradient step. Okay? So I'm going to come up with a new algorithm, which is the first order Lagrangian method. Xk plus 1 equals to xk minus alpha L xk lambda k. Lambda k equals to sorry, lambda k plus 1 equals to lambda k plus c hxk. So I just need to pick alpha and c. Once I pick alpha and c, I'm done. I don't have to do complicated stuff. As is always the case, alpha will be sufficiently small and c will be sufficiently big. C could be equal to 1, 2, 5, but not 1 million. And you've seen what happens if you pick a very large C, what kind of results you get in solving problems of this type. What does this algorithm converges to? How do you know what this, what the limit point of this particular, so let's assume that xk has converged. Let's say this thing is converged. We know from some of the previous results that if xk is picked in this fashion, then lambda k plus 1 converges to lambda star, right? So if this particular algorithm is converging, what is satisfied by that particular point, limit point? So x infinity equals to x infinity minus positive number multiplied by the gradient. So the gradient must be equal to 0. Lambda infinity equals to lambda infinity plus c h of x infinity, which means that c is a positive number, so this must be equal to 0. So if xk lambda k converges to x bar lambda bar, then gradient of x of Lagrangian is equal to 0 and h of x bar is equal to 0. So it seems to be converging to the right point, which is the first order, which satisfies the first order stationary condition. And it's a gradient descent, not a gradient ascent. So it's a descent method. So this must be the minimizing, or rather the first order necessary condition for the argument. Awesome. So my gut feeling is that if this algorithm converges, it's going to converge to a point which is desirable point. It's desirable because it satisfies the first order necessary condition for the argument, and it also satisfies the fact that it's on the manifold h of x equals to 0, as a result of which it satisfies the constraint. Now the only question is, why should this be the case? That's the only question we need to answer. So I started with a complicated algorithm, I simplified the algorithm, I analyzed that if this algorithm converges, I'm at a desirable point. Now the only question to answer is, why does this algorithm converge? Okay? And in order to prove that this algorithm would converge, I have to, I'm going to introduce an important result, and I think the purpose of this class is to actually talk about that important result, which is Banach contraction mapping theorem, and its implication on not just this algorithm, but the entire field of optimization. Banach contraction mapping. This is my favorite theorem, by the way, in life. I love this result. So what is the setting? I have X, a subset of Rn. It's a closed set. I have a mapping T from X to X. I have a mapping T that takes as a point in X and maps it to another point in X. And this one satisfies a very specific property. So for any norm, No, I don't want to say any norm. So pick a norm. On Rn, and T satisfies T of x1 minus T of x2 is less than equal to gamma times x1 minus x2. Okay, so the book is using rho, so I'm going to use rho. I don't think we have used rho so far. This rho will be spectral radius of a matrix in some time, but for now just assume that this T satisfies this condition and rho is strictly less than 1. Okay, this particular setting is clear. I have a closed set. Closed set looks something like this. This is my set capital X. Now I have to draw the same set again. I pick a point x1. This is my T of x1. I pick another point x2. This is my point T of x2. So every point within this set is mapped to a point within the set itself. It's not getting mapped to a point outside the set. But there is a specific property that it satisfies. So I'm going to pick any norm, pick some norm on Rn, okay? So the important thing to note is that this mapping T is going to, so this kind of map is known as a contraction. So the mapping T is going to be a contraction with respect to a specific norm. So once you pick a mapping T, you have to also define a norm under which that particular T would be a contraction. And so if you change the norm, T need not be a contraction in the new norm. But anyways, assume that you have picked a norm and T satisfies this contraction property. What is this property? So if I look at the distance between Tx1 and Tx2, which is this distance is less than equal to some factor less than 1 times x1 minus x2. So x1 minus x2 is this distance. So if this distance is d, this distance is less than rho times t. Okay, is the setting clear? Any question? And what I'm going to show in some time is that this particular map is a contraction map. So we'll get to it towards the end of the class today. But right now the setting is clear. I have a mapping T. This could be an algorithm, a mapping induced due to an algorithm. I'm picked a norm such that T is a contraction with respect to that particular norm, with a contraction coefficient less than 1. So this is contraction coefficient. And T is known as a contraction map. Okay, so what is T doing? So T is taking this closed set and it's squeezing it, it's contracting it. Okay, so if you keep doing it infinite number of times, what's going to happen? So at every point of time, you're taking a set, you're contracting it. Then you apply the same algorithm again or same mapping again, you're contracting it further and you're contracting it and you're contracting it. And this contraction is by a factor rho. Okay, So you're not just making it smaller, you're actually really reducing the volume by a very specific factor rho at every point of time. So what's going to happen in the limit? The whole set is going to collapse to a point. Okay, that's what the result is. So the theorem is, so define xk plus 1 equals to t of xk. X naught is in the set capital X. Then t has a unique fixed point x star such that t of x star equals to x star, and b xk converges to x star as k goes to infinity. This x star, of course, lies in X. X star lies in capital X. Okay, so what are we looking at? So I'm starting from some initial point in this set capital X. I'm iteratively applying the same map again and again. I get a sequence xk plus 1 equals to t of xk. So I'm getting a sequence. In optimization, typically you apply a gradient descent algorithm or you apply a mirror descent algorithm again and again on a point, and you get a sequence of points. It turns out that a contraction operator, a contraction map, has a unique fixed point x star such that t of x star equals to x star. So a fixed point of an operator or fixed point of a map is a point which is not moved by the mapping itself. So I am looking at x star, I apply the map t again, I get the same point. Okay. And the second one is that this particular sequence that I'm generating is going to converge to that fixed point as k goes to infinity. So let's look at an example of this map. So my t of x equals to x minus alpha gradient of fx, right? And my x is in Rn itself. T of x is equal to ax plus b, and this is of course in Rn. So again, x is equal to Rn. Okay, so this is the gradient descent, the steepest descent algorithm. I start with x1, and then I pick the steepest descent with constant step size alpha, and this one converges to which point? The point at which the gradient of f is equal to 0, right? That's the fixed point. When is t of x star equals to x star? When gradient of fx star is equal to 0. This thing converges to what point? What does Txk converges to? It converges to x star equals to Ax star plus B, which is I minus A inverse B, right? This is something that was something that you used in your previous assignment. So this is the fixed point. This x star I minus A inverse B is a fixed point of this operator T. And this one holds only if rho of A is strictly less than 1. This rho is the same as this rho here. Okay, so these are the cases where this fixed point theory is applied. And now we are going to prove this particular theorem. Okay. In momentum method also, or in Nesterov's accelerated gradient method, we also had another fixed point operator T in that case. So again, you have done assignments and you have used these fixed point operators or fixed point maps, sorry, the contraction maps multiple times in your assignment. Today you will realize why in all those assignments, whenever you ran the iteration, it converts to the optimal solution. Why did that happen? So today we are going to actually study the proof of that approach. Okay, so part A. T has a unique fixed point. So let's say I have two fixed points, x1 star and x2 star. Such that T of x1 star equals to x1 star, T of x2 star equals to x2 star. Okay, so then what do I have? T of x1 star minus T of x2 star norm is less than equal to rho times x1 star minus x2 star, and this is equal to x1 star minus x2 star. So let's assume that T has multiple fixed points, x1 star, x2 star, x3 star, whatever. So I'm just picking two of those fixed points. And I notice that x1 star minus x2 star is less than equal to rho times x1 star minus x2 star. When can that happen? When can something be less than a factor less than 1 times the something again? When that something is equal to 0, right? So this implies x1 star minus x2 star is equal to 0. When is a norm equal to 0? When the point is the same. So you have a unique fixed point. You cannot have multiple fixed points. Any questions on part A? So if you have a contraction map over a set X, then you have a unique fixed point X star within that particular set. So within this set capital X, there is a single fixed point of T. Okay. Let's look at the part B, which is the more interesting one. And this one is saying, what this one is saying is, no matter you come up with some algorithm, okay, assuming it's a first order algorithm, so you cannot use Newton's method, you cannot use contraction mapping theorem with Newton's method, but you can use it with other methods. So you come up with some sort of algorithm. As soon as you prove that that algorithm is contraction, with respect to some norm. So you will have to maybe spend some time figuring out what is the norm with respect to which it is a contraction. But once you prove that it is a contraction, you're guaranteed that your algorithm will converge to a point, to a fixed point of that particular map. So let's look at how do we prove the second result. The way to prove this result is, remember at the very beginning, I think in lecture 1 or 2, we talked about Cauchy sequences. And we said that if xk is a Cauchy sequence, then it converges. So all we have to do is prove that xk is a Cauchy sequence. So B prime xk is a Cauchy sequence. So I'm going to prove B prime, and because Cauchy sequences converge, I get the second part automatically. So what does Cauchy sequence mean? I'm going to look at xk plus m minus xk, xk plus m minus xk plus m minus 1, xk plus 1 minus xk, just by applying triangle inequality. Okay, so I use triangle inequality to look at the successive iterates and the distance between successive iterates. Now, there is a recurring theme here. We are looking at the difference between successive iterates. So let's look at what x2 minus x1 looks like. This is t of x1 minus t of x0, which is equal to, which is less than equal to rho times x1 minus x0. Okay, so x2 is tx1, x1 is tx0. I look at the difference, that's less than equal to rho times x1 minus x0. Let's look at x3 minus x2. T x2 minus tx1 less than equal to rho times x2 minus x1 less than equal to rho square times x1 minus x0. What do you notice? Yes, notice something?
I mean, it's the same, right? Except it's just, I mean, it just got shifted by one.
Yes.
Plus you just added the square.
Wonderful. So what is xk plus 1 minus xk? Less than equal to.
X0 minus.
Right? Rho raised to k x1 minus x0. Proof by induction. You can prove this result by induction. Okay, by now you are all experts in the principle of mathematical induction. You've used it in your assignments a couple of times. So by induction, you can prove this result. Now I have a whole bunch of stuff here, whole bunch of summations here of successive iterates. So let's try to get the expression. So this is less than equal to rho of k plus m minus 1 plus rho of k x1 minus x0. Oh, actually, I can write it as rho of k 1 plus rho of m minus 1 x1 minus x0. Anything rings a bell now? Does this expression ring a bell? So I have the first less than equal to sign by triangle inequality, second one by using this result of induction. Third one is equality, so this one is the same as this one. What about this summation inside the parentheses? What's that? Yeah. It's a geometric series, so what does this sum to?
1 over 1 minus.
Rho, right? 1 over 1 minus rho. So this geometric series, remember rho is a positive number. Rho is a positive number less than 1. So this geometric series, if I let m go to infinity, converges. And that limit is going to be 1 over 1 minus rho. So I'm going to have a less than equal to sign 1 over 1 minus rho and then times x1 minus x0. What's the definition of a Cauchy sequence? Any question so far before we proceed? So I'm going to erase this one. What?
Do we need to make m goes to infinity?
We don't have to make m go to infinity. I'm just using the fact that this is an upper bound on this, because I'm adding like a whole bunch of positive terms. So Cauchy sequence says xk plus m minus xk. So it's not letting m go to infinity. Okay. So I have xk plus m minus xk is less than equal to this. What's the definition of a Cauchy sequence? That for every epsilon greater than 0, there exists an epsilon such that xk plus m minus xk is less than epsilon for all k greater than equal to, well, k prime minus xk is less than epsilon for all k comma k prime greater than equal to n epsilon. This is the definition of Cauchy sequence. So I'm going to pick k prime to be k plus m, right? So I can pick whatever is the smallest of the k and k prime as k, and the other one could be k plus m, because now I'm increasing the value. M could go from 0 all the way to infinite, I mean, any natural number. So is this satisfied? What is my n epsilon here? I think I can pick n epsilon to be what? Log of, it's complicated. But the point is, I can make this number as small as I want to by picking k sufficiently large. So if I pick k to be greater than log of epsilon over log of rho, so it will be roughly equal to log of epsilon over log of rho, with some other factors also to account for this 1 over 1 minus rho term and x1 minus x0 term. So roughly after this n epsilon, I'm going to see that xk plus m minus xk is less than equal to epsilon times some constant. Whatever, I'm just going to let it, so there is some term that you have to divide epsilon by, but I'm sure you can do the math and you can figure out, you can convince yourself that xk plus m minus xk is less than equal to epsilon, or strictly less than epsilon, for all k greater than equal to and epsilon and m in the space of natural numbers. And so this implies that xk is a Cauchy sequence. Okay, so xk is a Cauchy sequence. Consequently, it has a limit. The limit must satisfy tx star equals to x star. So x star is a unique fixed point of t. So therefore, xk converges to x star as k goes to infinity. Okay, so that's the important result, Banach contraction mapping theorem. This theorem is at the heart of the field of reinforcement learning. It's at the heart of convergence of algorithms in optimization, convergence of algorithms in differential equations, convergence of algorithms on PDEs, partial differential equations, convergence of reinforcement learning algorithms, and so on and so forth. So it's just that this set X changes and this norm over the space changes depending on what application you are currently looking at. Okay, that's why I love this theorem. This is a theorem that is used across different areas. No matter what math classes you take, or what physics class or engineering classes you take, there will be some version of contraction mapping theorem that you will be using for proving convergence of something. And that convergence could be convergence of solutions of differential equation, convergence of algorithms, convergence of optimization methods, and so on and so forth. Okay, yes.
What type of mapping should the T be? Does it have to be like one-to-one?
No, it doesn't have to be bijective.
Oh,
It just has to be a contraction.
okay.
Okay. So remember that you have continuous function, then you have Lipschitz continuous function. This one is saying that it has to be Lipschitz continuous with the Lipschitz coefficient less than 1. Okay, so it's the same thing as saying that it's a contraction map. So a contraction map is a function with Lipschitz coefficient less than 1. Okay, and this has to be strictly less than 1. And the reason why it has to be strictly less than 1 is because this summation is only valid if rho is less than 1. Otherwise, this summation is not valid. You don't have convergence of geometric series if rho is greater than or equal to 1. But if rho is less than 1, then you can have this inequality. Okay. Now going back to our optimization framework, okay, how does this apply? So we know that T could be a gradient descent operation, like steepest descent operator. One thing to note here, an important point. So T has to be the same operator at every point of time. It has to be the same map. Now, if you're changing step size at every point of time, then you no longer have the same map, right? So at one point of time, you have xk minus alpha k gradient of fxk. At the next operation, you have xk plus 1 minus alpha k plus 1. So now alpha k has changed. As a result of it, you no longer have the same map. So you cannot apply these kind of analysis techniques to problems of that type, where you are changing the step size. Nonetheless, if you are keeping the step size constant, it gives you a good idea of whether the algorithm is going to converge or not with a constant step size. And there are obvious reasons why you would want to reduce or increase the step size, but those analysis techniques do not follow this contraction mapping result. Then you have to come up with a custom method, a custom proof for proving convergence of the algorithm. So how do we apply it to a general nonlinear function? Okay, so let's say you have xk plus 1 gxk lambda k plus 1 equals to hxk lambda k. Assume x star equals to gx star lambda star and lambda star equals to h x star lambda star. So define R star as gradient xc, gradient xh, gradient lambda g, gradient lambda h evaluated at x star lambda star. Okay, so now the result is if rho of R star is less than 1, then xk lambda k converges to x star lambda star as k goes to infinity if x naught lambda naught is close to x star lambda star. Okay, so this is the eigenvalue. Sorry, this is okay. Anyways, I'll let you guys write it and then I'll explain. Okay, so I come up with some algorithm for updating xk and lambda k as we had done in the case of first order Lagrangian method. Now the question that we were asking at the beginning of the class was under what condition would those algorithms converge? So if it converges, it converges to the right point. We had convinced ourselves of that. But the question is under what conditions would those algorithms converge? So turns out let's assume x star and lambda star are fixed point of g comma h. So g and h are my operators. X star lambda star is a fixed point of that operator. So my operator t is the joint operator g comma h, or I should really make it a column vector. So it would be g and h. That's my operator t, or contraction map t. So I have a fixed point of this operator. I look at the gradient of this particular operator at x star lambda star and assume that the spectral radius is less than 1. If the spectral radius is less than 1 of this particular matrix, then assuming you start sufficiently close to x star lambda star, you will converge eventually to x star and lambda star as k goes to infinity. So this iteration will converge to the desirable point. Okay, so a few things to note here. What does it mean that x naught lambda naught is close to x star lambda star? So remember, I was telling you about this closed set. So you have this entire space Rn, and let's say you have multiple fixed points, or Rn plus m, and you have multiple fixed points x1 star lambda 1 star, and then there is something here x2 star lambda 2 star. You have multiple fixed point of this operation. It turns out that there is something called a basin of attraction. What is the basin of attraction? It's a closed set around these points, and within these closed sets, this is a unique fixed point of the operator. Within this closed set, this is the unique fixed point, and if you start your x naught lambda naught here, it will converge to this point, and if you start x naught lambda naught here, it will converge to this particular fixed point. So this is known as the basin of attraction. This basin actually comes from wash basin, right? So what is wash basin? No matter where you pour the water in, it's going to go down the drain, right? So drain is the point where all the water is getting attracted to. So this is the drain, and this is where you are pouring the water, and it's taking a trajectory in order to get to the drain. So that's why it's called the basin of attraction. And within each basin of attraction, you have a unique fixed point of that particular operator, even though in the space you can have multiple fixed points. And the reason is, you have a contraction operation. It's a contraction operation with respect to one norm here. It's a contraction operation with respect to some other norm here. And you might have multiple such basins. So you can have another basin like this, and there will be a contraction operation with respect to some norm here. But there's no uniform norm over the entire space with respect to which it's a contraction. And therefore, in this particular case, it's not a global result. So for it to be global, you want this operator to be a contraction over the entire space with respect to the same norm. Okay, so that's not the case in general nonlinear optimization framework. Okay, but when the function becomes convex, then that becomes true. Okay, and then you have a unique, well, strongly convex. Then you have a unique fixed point over which all of these iterations converge, and then you have a global convergence guarantee. Okay, any questions so far? So very important things. I'm sure, assuming any of you are going for a PhD or you're already enrolled in a PhD program, this is going to be a recurring theme throughout your optimization curriculum, wherein you will try to characterize the basin of attraction, and then you will try to come up with the norm with respect to which the operator, the algorithm, is a contraction, and then you will show the convergence to the fixed point of that operator. Okay. So now that I know that there is going to be a basin of attraction of x star lambda star, and if I'm starting within that basin, then as k goes to infinity, I'm going to converge to that point. How does this result hold? Like, why do this result hold? So let's say I pick 2 points, x comma lambda and x prime comma lambda prime. So I have g of x lambda, h of x lambda, minus g of x prime lambda prime h of x prime lambda prime. Anyone knows what this is equal to? So this one would be some function this would be gradient x of g, gradient lambda of g, gradient x of h, gradient lambda of h, evaluated at some point x tilde lambda tilde times x minus x prime and then lambda minus lambda prime. So I have this point. Let me erase this. So this is my set capital X. This is my point x star lambda star. This is my point x and lambda. This is my point x prime and lambda prime. Okay. So I apply this operator g and h over x and lambda and x prime and lambda prime. I take the difference between the two. This is the mean value theorem, which says that you will have some point x tilde lambda tilde somewhere on this particular line. So let's say this is the point x tilde lambda tilde, such that the difference is equal to, okay, this is an equal to sign of the gradient at x tilde lambda tilde times x minus x prime and lambda minus lambda prime. All of you agree with this? Right? Mean value theorem. Okay, so I have Tx minus Tx prime is equal to some matrix times x minus x prime. Okay. How do I know that this is a contraction? So then I can take the norm. I don't know how I should write it. Maybe I'll write it this way. So I let Tx lambda x prime lambda prime norm is less than equal to the spectral radius, well, no, I think I want to make a point clear. So given R star, given this particular matrix, there exists a norm such that R star x is less than, well, it's not just x but x comma lambda is less than equal to rho R star x and lambda. Okay, so this is a result. This is a result from linear algebra. We haven't talked about this result, and the coming up with this particular norm is somewhat complicated, but it's there in advanced linear algebra books. So I'm just trying to recall that result without proving it. But for every matrix R star, you can construct a norm such that if you multiply r star by any vector, it's less than equal to the spectral radius of r star times the norm of the vector itself. Okay. Wonderful. So, oh, I think I'm over time. I'm so sorry. I got carried away. So I'm going to start from this particular point in the next class, and I'm going to talk about why exactly. There are some important issues to consider when you're looking at this spectral radius. So we'll talk about that in the next class.